The nature of rates examples is very often one that links to chemical experiments. So here we've got an experiment where we're going to measure the rate of a chemical reaction. First we need to understand what has happened. We put a certain amount, or certain volume rather, of hydrochloric acid over some zinc pellets, and we will produce hydrogen gas. That hydrogen gas will then fill up the syringe to various volumes of hydrogen gas. First, we're going to keep exactly the same mass of zinc in both cases, so that's a fixed variable. Our independent variable is we are going to change the concentration of hydrochloric acid. First, we're going to use 50 moles of 1 mole per cubic decimeter, and then 50 moles of 0.5 moles per cubic decimeter. And we're going to watch what happens. In the first experiment, we land up seeing that the gas increases. I choose the time over here. So the time remains fixed, and it is the amount of gas produced in that time that is my dependent variable. So after 10 seconds, 20 seconds, 30 seconds, 40 seconds, 50 seconds, by 60 seconds, I've got 60 milliliters of gas, and I see no further increase. That means that the reaction has stopped at that point. It has exhausted its materials. In the second case, I get 9, 17, 24, 30, 37, 42. You can see it's going slower. It's taking you, in the same periods of time, you're producing less gas. And it goes on for longer. It goes on all the way until 120 seconds, when again it stabilizes at 60 milliliters of hydrogen gas being produced. This shows me that my zinc pellets were my limiting reagent. In other words, the zinc ran out, because I've actually got different amounts of hydrochloric acid, but in the end I landed up with exactly the same amount of hydrogen gas being produced. So, firstly, when was the reaction complete in each experiment? In experiment A, it was complete after 60 seconds, whilst in B, you needed 120 seconds. Then it asks you to use the data to plot a suitable graph on the same set of axes. So first we label our axes. We're going to put time, because it's independent. I choose the time each time in seconds. And I would need to go up 10, 20, 30, 40. I don't have beautiful graph paper here, so I'm going to kind of go up 20, 40, 60, 80, 100, 120. And those must be nice and evenly spaced. And then I've labeled my axis, and then milliliters of hydrogen gas, and this goes up as far as 60, so I'm going to go 10, 20, 30, 40, 50, and 60, and I need to give my graph a heading, graph showing, and it's always y versus x, volume of H2 versus time. Underline. I then plot my points. So my first point after 10 seconds is for gas A is going to be 19. After 20 seconds, it has gone all the way up to 33. After 30 seconds, it has gone all the way up to 44. 52 at 40 seconds, and 58. And you notice that it is starting to taper off. It's not coming out as a straight line graph, and then I land up with lots of points up at 60. So obviously 0, 0 seems like a valid point, because when we have no time, we have made no gas, and I join those points together with a smooth curve. Looking at the next one, after 10 seconds, I've only got 9. After 20 seconds, I have 17. After 30 seconds, I've got 24. After 40 seconds, I'm up at 30. 50 seconds, I've got 37. 42. 47. You can see it's starting to taper off again here. 80. 51. 90 is 55. 100, 58, 120, 60, 60, 60. So this is a slower curve than the other one. What factor caused the rate change? It would have been the concentration of hydrochloric acid, because that was the only thing that changed. And how does this factor increase the rate of the reaction? Explain your answer in terms of collision theory. Well, what is concentration? Concentration is number of moles per volume. So if I've got more moles, so more moles means more particles, therefore more collisions, therefore more successful collisions, and therefore faster rate. Now the other thing we need to look at is how rates can be shown on a graph. The rate of the reaction is the change in concentration per time for either the reactant or the product. This is a definition and you're going to need to learn it. So if it is the rate of change of concentration, I will find that I can use the gradient to look at the rate all the time. Here, there's no further reaction taking place. The minute I've got an evened out graph of reactant and product, that is when the reaction has stopped progressing. Notice at the beginning, I am getting more and more product, and I get it very fast to start with, and then it slows down. The gradient of that graph gets less and less. And the reactants, simultaneously, I lose a lot of reactant to start with, and then I lose a bit less reactant, and a bit less reactant, and a bit less reactant. So the rate at any time can be determined from the gradient of a concentration time graph of the reactants and the products. So that the steepness, remember what gradient is? It is the steepness, is going to tell me more or less how fast the reaction is proceeding. Now obviously as a reaction proceeds, initially there's lots of particles reacting, so it goes fast. And then some of the particles have been used up. So in terms of collision theory, there are less particles colliding as the reaction reaches completion, and that is why the reaction rate slows down as you get closer and closer to completion. The relationship between a rate time graph, concentration of product versus time, is similar to velocity time and acceleration time. In other words, if I've got constant rate increase, that means if I've got a constant gradient, the concentration of product is increasing at a constant rate, then my rate is constant. When I have got no increase in product, I have got no rate. And so you can actually relate these two graphs to one another.